Hi, this is Dane Quinn, and I'm from the University of Akron. Today we will be presenting a lecture on momentum balance for engineering mechanics dynamics. So these are the equations of motion. This is what it's all about. Dynamics is, of course, the application of the laws of mechanics to develop the equations of motion that describe the response of some mechanical system to external effects. So in particular, we want to take the external forces that exist on, say, an object B. Right, so we'll kind of represent these by some of the forces, as well as the external moments. Right, so those we'll kind of represent by a couple. Some of the moments that act on this rigid object, and we talked about what it meant to be rigid in an earlier lecture, to help us describe the motion of that object. So here in this class we're focused on planar motion, right? So that's going to significantly simplify the resulting equations, and in particular all points are constrained to move in a single plane of motion. So we think about that as the sort of plane of the paper or the computer screen or whatever you're viewing this on. So this object B has to stay in this plane. So now, in terms of linear momentum balance, really let's look at a mass element, dm, right? Because the equations for momentum balance, as postulated by Newton and dealt with in earlier lectures, are only valid for a particle, right? So a point mass, something with zero size but finite mass. But on that little mass element dm, of course, we have the sum of the forces, right? So we're going to describe the forces that act on that mass as F dm. And so linear momentum balance for an individual particle says that F dm is equal to the mass, which of course is dm, right? It's a little bitty thing, times the acceleration of that mass element, a dm. So now, in terms of the object itself, recalling back to our discussions on planar kinematics, we can write the acceleration in terms of the motion of the object and the relative position of dm in terms of that object. So here, the acceleration of dm is defined as the second derivative of some position vector. Right? So we'll describe that position vector as r of dm with respect to O, where O is some origin out here in the ground. Then we have this position vector. Again, this is where this little mass element is in the object. So we have r of dm with respect to O. So we're going to write this acceleration in terms of another point fixed on the object, which we'll call A. So then we have the position of A with respect to O, and we have the position of dm with respect to A. So that this acceleration is the acceleration of A plus the angular acceleration of the object itself cross r dm with respect to A plus omega cross r. So this was our result from planar kinematics for the acceleration of any 2 points fixed in an object. And of course, we're choosing A to be fixed in the object, and the mass element is also fixed in the object because the object is rigid. So now continuing on, we're going to look at the total force acting on this mass element as composed of 2 parts. Right? And those 2 parts are going to be one component that comes from external effects. Right? So we'll say that this is F dm external. So these are forces that are applied to the object at this mass element. And then the second force that we'll look at is going to be internal forces. Right? So that's going to be a force that is applied to the mass element, essentially from all the other mass elements in the body. And it's going to represent things like internal stress, and really this is the force that sort of holds the object together. So again, we have external effects and internal effects. So on the object itself, right, we have sort of the equal and opposite force from this component. So that's going to be minus F dm internal. And of course these have to balance out because of Newton's third law. So now we'll write F dm as the sum of the external forces and internal forces. So now what we can do is take linear momentum balance, right, for this mass element. F dm is dm times a dm, and we will integrate that over the entire object. So I'll take all of these little equations of linear momentum balance for every single particle and I'll add them together. And so as a result, we can write this as, well, the force was F dm external plus F dm internal. The acceleration we wrote as acceleration of A. Right, so remember we had a point A over here. We have our origin there. R dm with respect to A. And so we can write this as the acceleration of A plus alpha of the body cross r of dm with respect to A plus omega cross r. dm, and then again we're integrating this over the body. So really we've just taken this decomposition of the forces, put it in on the left hand side. We've taken the acceleration for the mass element here and written that in terms of the acceleration of some other point A on the right hand side. So now let's take and distribute this integral through. So again, we're integrating over the body, so we have the integral of the external forces plus the integral of the internal forces equals. Now here what we find is that the acceleration of A is constant over the body. It's not constant in time, but again this is an integral over the body itself, so it's a volume integral. So regardless of which mass element I choose in this integration, the acceleration of A is still the same, right, because it's a property of this single point. So that means that in this acceleration of A integral term, I can actually factor this out. So I get A times the integral over the body of dm. Likewise, for the next term, the angular acceleration is constant over the body. So I can write this as alpha cross, but now r dm with respect to A certainly depends on the choice of the mass element. So I can't sort of factor that out of the integral. So I've got to leave that in. So we have the integral over the body of r dm with respect to A dm. And then for this last term, the angular velocity is constant, so I can write this as omega cross omega cross, and then we have the integral over the body of r dm with respect to a. So here we just simply integrate all of the mass elements. Now we're integrating the position of each mass with respect to a in these two terms. And then these are the integrals of the external and internal forces over the body. So now we can simplify this significantly, right? In particular, we haven't said which point A we're going to choose. Up to now, A is just some arbitrary point. But now we can be a little bit clever, and we can choose A so that that integral term, the integral of the position of each mass element with respect to A, dm, well, we can choose that to be equal to 0. Right? So this is basically a specific point on the body for which this integral vanishes. And really, the physical interpretation of this is that A is the mass center of the body. So we often describe the mass center as G. It's just a common notation, but it helps to keep different points straight. So whenever you see a G attached to a point on a body, it's probably the mass center. And this is, in fact, the definition of the mass center. The mass center is defined as that point which the integral of the position of all the other masses, of all the mass elements, vanishes. So again, if we choose A to be the mass center, then all of those integral terms, let's go back and look at this slide, this term goes away, and this term goes away. So now, the other thing that we have going for us is that when integrated over the body, the internal forces vanish. So the net internal force vanishes. So now if we were to consider a rigid body as composed of just a bunch of particles, and we assume that each particle interacted according to Newton's third law, right, so action-reaction, then we can show that all of those sort of internal action-reaction forces equilibrate, right? So they ultimately, when I add them all together, they vanish. Now, this is not quite the way that we understand how atoms and field theory works, but it's a good enough approximation, right? And we assume that it's true. Now, when I look at the external forces, well, that's just the integral of the body of all the forces that are applied, right? So really, this is just adding up all of the forces that are applied to the body, right? So we write that as the sum of the forces acting on the body. And this integral looks like the total external force. So, as a result, let's go back and write the expression from the previous slide. Sum of the forces external plus sum of the forces internal. That equaled A of G, because now, remember, we're choosing the mass center as the point for our acceleration of each mass element. And then we have alpha cross r dm with respect to G. And then plus omega cross omega cross r. So again, this was the expression from the previous slide. And as a result, this piece goes away, this vanishes, and this vanishes. So all we're left with is the following. Sum of the forces acting on the body is equal to, well, this is just the integral of all the little mass elements. So this is the total mass of the body times the acceleration of the mass center. So again, when I integrate all of the mass elements over the body, I just get the mass of the body. And this is linear momentum balance. Very simple. It looks like the equation for linear momentum balance that we had for a particle. The only difference now is that here the acceleration is a specific point, and it's the mass center of the object. So we have a point O, an origin fixed in the ground, and I want to find the acceleration of the mass center, right? So now this is the position of the mass center with respect to the origin. So I want to find the acceleration of this single point, and that is going to be equal to, well, multiplied by the mass, the total force acting on the object. So we now have the equations for linear momentum balance. And again, it ends up looking like sum of the forces is mass times acceleration. So in addition to linear momentum balance, we can describe equations of motion for the rotation of the object as well through angular momentum balance. So looking back at our little mass element dm, and the forces that are applied. So this will be F dm. Then angular momentum balance is defined as the cross product of the position of dm with respect to A with the equations for linear momentum balance. So that's F dm is dm times the acceleration of this element. Again, the idea is here we have a point A, and of course we have our origin over here. So this is the position of dm with respect to the origin. Then we have the position of dm with respect to A. And we'll take sum of the forces as mass times acceleration, linear momentum balance on this element, and we'll take the cross product of that with the position of dm with respect to A. So this is angular momentum balance for any individual particle. And then just like before, we will write F dm, right? So we'll break the force into a component due to external effects and a component due to internal effects. Again, these are applied forces, and these are internal forces that essentially keep the object rigid. So, for example, internal stress. So we will integrate this over the body, just like we did for linear momentum balance. So we have position of dm with respect to A cross the force which again is written in terms of external and internal components. And then the position cross the acceleration. And so again, the acceleration we'll write in terms of this point A. And at the moment, A is arbitrary. It's not necessarily the mass center, but instead it's any point on the object. So alpha cross R and omega cross R. Again, integrated over the body. So now, looking at the left-hand side, the cross product of the position with respect to the external forces, well, that's just going to be the total external moment acting on the body. So these are the sum of the moments about point A. Then the second part, r dm with respect to A, cross the internal forces, well, that represents the internal moments acting on the object about point A, and that we actually assume to vanish. Again, here if we had an object composed of particles and forces interacting between those particles that obeyed Newton's third law, you could show that this expression would vanish identically. Again, we just postulate this and assume that the internal moments vanish. So then, looking at the right-hand side, a lot of this will simplify again, right? But in particular, for planar objects, we have the last term vanishing. So r dm with respect to A cross omega cross r dm with respect to A equals 0. And this is only for planar objects. If we have objects moving in space, three-dimensional motion, this term would not vanish necessarily. But again, when we focus on planar objects, then this term is equal to 0. And the reason is that omega cross r, again, if omega is out of the plane and r is in the plane, that is something perpendicular to r. And then we take another cross product with omega. Remember, the centripetal acceleration was directed opposite to r dm with respect to A. So now this vector is parallel to r dm, and we're crossing that with r dm itself, right? So we're taking the cross product of two parallel vectors, which equals 0. And as a result, angular momentum balance simplifies to the following form. Sum of the moments about point A acting on the body is equal to the integral of r dm with respect to A cross the acceleration of A. So that was the first term. And then we have the integral over the body of r dm with respect to A cross alpha cross r. So this is what angular momentum balance reduces to. Now we're going to do the same thing that we did before in terms of different points. So let's assume that A is here, And let's add the mass center. I'll sort of offset it up there for presentation. But let's assume the mass center's there. So now, this vector from A to dm is here. So r of dm with respect to A. Then we'll have a vector from A to G. So this is the position of G with respect to A. And then we have the position of dm with respect to G. So we'll again write this position vector the position of the mass element with respect to A be written in terms of the position of G. So it's the position of G with respect to A plus the position of the mass element with respect to G. So when we do this, again, recall that the integral of r dm with respect to G acting over the body is equal to 0, right? Because G is exactly the mass center. So now when we take this and we introduce it into this previous expression, this first term simply becomes r of G with respect to A cross the mass of the body times the acceleration of A. We can take this, we can put it in, and then this component vanishes. And then everything else is constant with respect to the object, so we just end up with the mass. But then we still have this last term. So it's r cross alpha cross r. So now let's try to evaluate this last term. So now for planar objects, let's put, say, directions E1 and E2 fixed in the body. So we can go and describe the position of dm with respect to A, right, in terms of these directions. Right, so we'll let S1 and S2 be the components. So the position of dm with respect to A can be written as S1 in the E1 direction and S2 in the E2 direction, where S1 and S2 are obviously fixed. And then the angular acceleration of the object, we can write that as alpha in the k direction. Right? So here, the k direction would be out of the plane. For planar dynamics, the angular acceleration is always perpendicular to the plane of motion. Right? So it's only going to be in the k direction. And as a result, what we find is that r dm with respect to A cross alpha cross r dm with respect to A, right? So this term inside the integral ends up as s1 squared plus s2 squared times alpha in the k direction. Like I said, you just take this, introduce it in here, and work it out, and this is what we get. So notice that s1 squared plus s2 squared is actually the magnitude squared of this vector. Right? So it's the magnitude of r dm with respect to A squared times the angular acceleration itself. So alpha of the body. And so finally, we define this magnitude as simply s. Right, so we'll just call it the length between A and the mass element dm as s, so that this whole integral just becomes a function of s. This whole thing becomes the angular, or the integral over the body of s squared times alpha dm. Right? But of course alpha is constant, so we can factor that out, and we're just left with the integral over the body of s squared dm times alpha. So now this piece in brackets, it's just a property of the shape and mass distribution of the object, right? It doesn't depend on the motion. It's simply the integral of each mass element, right? The distance between each mass element and the point A squared integrated over the body. Again, it's something we can calculate ahead of time, where we don't need to know how the object moves in order to calculate this integral. And so this is a property of the object, and it's plays an equivalent role as the mass of the object. And so it gets a name, right? And it's referred to as the moment of inertia of the body about point A, right? So I is the moment of inertia of the body about point A. And of course, as we change point A, right, we would have different values for this moment of inertia, right? And later on, we'll do a separate video lecture that deals specifically with this moment of inertia. But for now, just know that it's a property of the object, and it plays the equivalent role of the mass in terms of angular momentum balance and ultimately the rotation of the object. So now, for planar objects, angular momentum balance reduces to sum of the moments about A acting on the body is r of g with respect to A cross mass times the acceleration of A plus the moment of inertia of the body about point A times the angular acceleration of the body. And this is the most general form for angular momentum balance. However, there are three cases where this first term vanishes, and we're left with sum of the moments is equal to I alpha. So case 1 is if RGA vanishes, which means that A is the mass center. Right, so if we take sum of the moments about the mass center, then R of G with respect to A equals 0. Because again, G and A are coincident. And so G and A are coincident. Right, so basically we've taken A to be equal to G. And we have sum of the moments about the mass center is the moment of inertia about the mass center times the angular acceleration of the body. And this always works, right? Is we can always take A to be the mass center, and we can always find this equation. Now, the second case where this vanishes is if this term goes away, right? So let A is fixed in the object. So that was a requirement of the point that we were choosing. And fixed in the ground. So as a result, the acceleration of point A is equal to 0. And we'll refer to A as O. So O is a suitable origin for our acceleration calculations. And with this, sum of the moments about point O is equal to the moment of inertia about point O times the angular acceleration of the body. So that's the second case. And again, this happens when the object is pinned at O, for example. So the third and final case is a special case, right? But it is one that happens quite frequently in certain situations. So there we're looking at a case where the position of G with respect to A, so the position of the mass center with respect to the point that we're taking the moments about, is actually parallel to the acceleration of that point. And then as a result, we're taking the cross product of two parallel vectors. And so it happens naturally when we take a disk that is rolling without slip on the ground. All right, so we have a uniform disk. Let's put the mass centered at the center of geometric center of the disk, and then let's look at the contact point as point C. So we have a disk rolling without slip on the ground. And in this case, one can show that the acceleration of point C is actually directed toward the center of the disk. Right? So again, R of G with respect to the point that we're taking the moments about is parallel to the acceleration of that point. And so in this case, we again find that sum of the moments about point C is equal to the moment of inertia about point C of the body times the angular acceleration of the body. So again, in these three cases, this general form for angular momentum balance simplifies because the first term representing this cross product drops out. So it's when the position of G with respect to A is equal to 0, right? So A is exactly the mass center. Or A is fixed in the body and fixed in the ground, so its acceleration vanishes. Or finally, if these two vectors are parallel, and that happens when we have a disk rolling without slip on the ground, then in all three cases we have this simplified form. So that is our discussion and derivation of momentum balance, linear and angular momentum balance, for a rigid object undergoing planar motion. And this will be the basis for much of the work that we do following, and in particular deriving equations of motion for the dynamics, the planar dynamics of rigid bodies. Thank you very much.